Sit down for a second, because today I want to tell you a story that every time I think about it gives me chills. It's the story of why we can finally start dreaming about a Voyager 3. Voyager 1 and Voyager 2 are, without exaggeration, two of the most successful machines ever built by human beings. They reached every gas giant in the outer solar system. They sent us the first close-up photographs of Jupiter, Saturn, Uranus, Neptune. They crossed into interstellar space. They're still out there right now transmitting data home from billions of miles away. But what almost nobody talks about when they tell the Voyager story is just how absurdly lucky we got. How razor-thin the window was. How close we came to never doing it at all. Because the Voyagers were a miracle of timing. They launched during a planetary alignment that occurs, brace yourselves, once every 175 years. A cosmic configuration where Jupiter, Saturn, Uranus, and Neptune all happen to sit in roughly the right positions for a single spacecraft to slingshot from one to the next, picking up free velocity at each encounter. Miss that window, and the entire mission would have been impossible with the chemical rockets of the era. Impossible. Not difficult, not expensive, impossible. And the next time those planets line up that way, the year 2152. Yeah, you heard me right, 2152. So the question that comes up over and over and over again in the comments under every single Voyager video, the question I get every week, do we really have to wait another 125 years for a successor? Are we really stuck? Why can't we use modern technology and go now? And the answer that lights me up like a Christmas tree every time I think about it, is in an engine that doesn't burn fire. It burns electricity. And it could change absolutely everything about how the next Voyager travels through deep space. Let's take a step back together, because to understand why a Voyager 3 mission has been almost impossible to design with traditional rockets, we need to look at how the originals actually traveled. And the answer is going to surprise you. Voyager 1 and Voyager 2 were essentially gliders. Yes, gliders. They're chemical rockets fired for a short time during launch, and then almost never again for the rest of the entire mission. The bulk of the speed didn't come from their engines at all. It came from the planets themselves. Here's how the trick works. When Voyager 1 passed close to Jupiter, the gas giant's enormous gravity bent the spacecraft's path and accelerated it like a sling. The same trick worked again at Saturn. For Voyager 2, the gain was repeated at Uranus and Neptune. Each flyby added kinetic energy without spending a single drop of extra fuel, because the spacecraft was effectively stealing a tiny bit of the planet's orbital momentum. The planet slows down by a microscopic amount. The probe slingshots away like a stone from a catapult. This technique is called a gravity assist, and it is no exaggeration the only reason any human-built object has ever escaped the solar system. Voyager 1 left Saturn cruising at about 17 kilometers per second. That's roughly 38,000 miles per hour. Right now, at this very moment, as you're watching this video, Voyager 1 is still moving at that speed. The fastest heliocentric speed any spacecraft has ever maintained, ladies and gentlemen, and the entire amount came from the planets. Not the engines, the planets. Now here comes the bad news. Without that 1970s alignment, a chemical rocket simply cannot replicate this. The fuel mass required to reach interstellar space on a direct chemical trajectory is so enormous that the rocket would need to be larger than anything ever built by human hands. The math just doesn't close. It doesn't close. Which means a 21st century interstellar mission needs a fundamentally different kind of engine. Something that doesn't depend on a single brief burn at launch and doesn't require a 175-year planetary window. An engine that can keep pushing the spacecraft for years on end, slowly building up a velocity that the original Voyagers could only dream of. That engine already exists. It's been quietly running on real missions for over 20 years, and almost nobody is talking about it. All right, folks, buckle up, because this is where things get genuinely magical. An ion engine works on a principle so simple that the first time someone explained it to me, I literally laughed out loud. It sounds like a magic trick, but it's real. It's running on spacecraft right now. Here's how it works. You take a tank of heavy noble gas. Almost always xenon, because xenon atoms are large and easy to ionize and chemically inert. You strip an electron off each atom, leaving a positively charged ion. Then you accelerate those ions through an electric field at speeds that would melt a chemical rocket nozzle. We're talking about ions shooting at the back of the spacecraft at around 90,000 miles per hour, or about 145,000 kilometers per hour. And by Newton's third law, the spacecraft itself gets pushed in the opposite direction. Now here's the part that confuses everyone the first time they hear it. The thrust produced by a single ion engine is tiny, microscopic, comparable to the weight of a sheet of paper resting in the palm of your hand. A chemical rocket can produce thousands of times more force in a single burst. So why are we excited? Because the comparison misses the point entirely. A chemical engine is a dragster. It produces immense thrust for a few minutes, then runs out of fuel and coasts forever after. An ion engine is a marathon runner. It produces a whisper of thrust, but it keeps doing so for years without ever stopping. Year after year, that whisper adds up and up and up. NASA's next thruster, the evolutionary xenon thruster, has run continuously in vacuum chamber testing for over 48,000 hours. Let me say that again, 48,000 hours. That's 5.5 years of uninterrupted operation, consuming about 860 kilograms of xenon over that whole period. A conventional chemical rocket would have needed roughly 10,000 kilograms of propellant to deliver the same total impulse. 10,000. The ion engine does the same job with 1/10 of the fuel mass. 1/10. And here's where the cumulative speed kicks in. The Dawn spacecraft, which used the older N-Star ion thruster to orbit 2 asteroids in the main belt, Vesta and Ceres, achieved a velocity change of 11.5 kilometers per second over its mission. More than any chemical spacecraft has ever accomplished on a single fuel load. Ever, anywhere, with 1 tank of xenon. So now imagine a modern ion-powered Voyager 3. Given a few years of continuous thrust, it could easily exceed the speed of Voyager 1 and keep going. Where the originals are coasting at 17 kilometers per second, Voyager 3 with sustained ion propulsion could realistically push past 40 kilometers per second and just keep accelerating and accelerating and accelerating. Same destination, different physics. The engine doesn't need a planetary alignment. It needs time. Now here's where things get really, really interesting, because this part connects to one of the most exciting questions I get in the comments. Why does every probe we send seem to travel along the same flat plane? The truth is, the original Voyagers had no real choice in their direction. None. Their trajectories were dictated by where the giant planets happened to be sitting at the time. Voyager 1 had to swing past Jupiter to reach Saturn. Voyager 2 had to swing past Jupiter and Saturn to reach Uranus and Neptune. Each leg of the trip was constrained by orbital mechanics that depended entirely on planetary positions. They went where the gravity slingshots took them. End of story. A Voyager 3 powered by ion engines does not have this problem at all, because it can thrust continuously in any direction it chooses. It's no longer tied to the ecliptic. There's no need to rendezvous with a gas giant or bounce off Jupiter to reach the outer solar system. The spacecraft can simply accelerate toward whatever target the mission planners want, including targets that are completely impossible to reach with gravity assists alone. And listen carefully, because this is where ion propulsion connects to something incredible, something so audacious it gives me goosebumps every time I talk about it. The vertical escape, the ability to send a spacecraft directly above or below the sun, into regions of space that no probe has ever visited because they sit perpendicular to the disk of the planets. With a chemical rocket, this kind of polar mission was almost impossible. The only way out of the ecliptic was the Ulysses approach, which we covered in detail in a previous video. A spacecraft had to launch all the way to Jupiter and use the gas giant as the gravitational lever, bending its trajectory upward and accepting years of detour just to reach a tilted orbit. Years of detour, friends. Years. Just to look at the sun from a different angle. With ion propulsion, the math changes completely. Steady thrust over time can slowly raise the orbital inclination of a spacecraft until it reaches the polar regions of the sun without needing a Jupiter flyby at all. And for the first time in human history, for the very first time, the geography of the solar system would no longer dictate where we can go. Voyager 3 could be aimed straight at interstellar space in any direction we like. The galactic center would be one possibility. Another would be chasing the constellation Hercules, where the sun itself is heading. There's also the option of dropping the spacecraft out of the bottom of the solar system into the unexplored void below the ecliptic. The choice would belong to the mission planners, not to the planets, to the planners. Okay, but, and there's always a but in this kind of story, isn't there? Ion engines have one stubborn weakness. They need electricity. A lot of it. Every existing ion-powered mission, from Deep Space One to Dawn to the Psyche asteroid probe, has relied on solar panels. Sunlight hits a large array. Photovoltaic cells convert it to electric current, and that current ionizes and accelerates the xenon propellant. The arrangement is called solar electric propulsion, and inside the inner solar system it works beautifully. Beautifully. The trouble starts as you move outward, and I mean serious trouble. Sunlight obeys the inverse square law. Translation: double the distance, quarter the power. By the time a spacecraft reaches Jupiter, the available solar power has dropped to about 4% of what it had near Earth. 4%? At Saturn, it's close to 1%. Past Pluto, photovoltaic panels become almost decorative, generating barely enough current to keep instruments warm, let alone power a thrusting engine. Any ion-powered probe that wants to keep accelerating in deep space has to find its electricity somewhere else. And the answer NASA has been pursuing is something that, when I first read about it, made me sit up straight in my chair. It's called nuclear electric propulsion, or NEP for short. The idea is to put a small fission reactor on the spacecraft. The reactor generates heat continuously, regardless of distance from the sun, and that heat is converted into electricity that powers the ion engines. It's the same principle as a nuclear power plant on Earth, miniaturized down to fit on a probe. Engineering, ladies and gentlemen, just pure, beautiful engineering. And here's the part that will absolutely blow your mind, because this is no longer just a paper concept. In March 2026, just a few weeks ago basically, NASA officially announced the development of Space Reactor 1, nicknamed Freedom. And Freedom will become the first nuclear electric propulsion interplanetary spacecraft in the entire history of human civilization. Its first mission, called Skyfall, will launch toward Mars in 2028, carrying small helicopters to scout the Martian surface. Freedom uses a 20-kilowatt fission reactor with low-enriched uranium, mounted at the end of a long boom to keep its radiation safely away from the rest of the spacecraft. A real, working, flying nuclear reactor in space in 2028. Now, yes, Freedom is a Mars demonstration mission, not a deep space probe. I'll be the first to admit that. But it is the proof of concept that an ion engine and a small reactor can fly together. Once that architecture is validated, once we know it actually works in the real environment of space, scaling it up for a true Voyager 3 becomes a straightforward engineering problem rather than a moonshot. The pieces are falling into place. The ion engine is mature, and the reactor technology is being flown for the first time. Within a decade, 10 years, friends, 10 years, the combination of the two could make a real Voyager 3 mission possible, with no need to wait for the next 175-year planetary window. And now we get to the part of Voyager 3 that has absolutely nothing to do with engines or reactors. Nothing. And yet it might be the part that 50 years from now, our children will remember more than any technical specification. The golden record. Attached to the side of both Voyager 1 and Voyager 2, there is a gold-plated copper phonographic disc, 12 inches across, weighing barely a kilogram. And on that disc, on that single disc, Carl Sagan and a small team at Cornell University in 1997 encoded 116 images of Earth, 90 minutes of music ranging from Bach to Beethoven to Chuck Berry, the sounds of wind and rain and whale song, and spoken greetings in 55 languages. 55 languages, friends. A message in a bottle thrown into the cosmic ocean on the very small chance that some other civilization might one day find it. Now here's the thing. The Voyagers will not encounter another star system for at least 40,000 years. Let me say that again, 40,000 years. And the probability that the record will ever actually be played by an extraterrestrial intelligence is, statistically speaking, essentially zero. Sagan and his team knew this from the beginning. The golden record was always less about contacting aliens and more about looking at ourselves. a mirror held up to humanity showing what we choose to remember about who we are. Which raises the most beautiful question of all. If we build Voyager 3 today in 2026, what would we put on board? The choices would be radically different. The 1977 record had to fit on physical analog media, a literal vinyl disc with grooves played by a stylus. A modern equivalent could carry petabytes of data, photographs, videos, the complete works of every major language, the genome of every species we have ever sequenced. The original record also deliberately avoided showing war, disease, or anything dark, presenting only the best of humanity. A 2026 version could choose to include those truths. And honestly, that choice, what we leave in, what we leave out, would say something profound about how we as a species have changed. But here's the part that nobody talks about enough. The United States is no longer alone in this race, not by a long shot. China has been quietly developing a mission called Shensuo, formerly known as Interstellar Express. The plan? Send 2 or 3 probes out of the solar system, one toward the nose of the heliosphere, one toward its tail. Target reaching 100 astronomical units from the sun by the year 2049. And the date 2049 is absolutely not random, my friends. It marks the 100th anniversary of the founding of the People's Republic of China. The 3rd probe in the Shensuo program, if approved, would use a nuclear reactor for power, exactly the kind of architecture that ion propulsion enables. Europe is also studying its own designs, and there's even a NASA interstellar probe concept being developed at Johns Hopkins APL that aims to reach the heliopause in 15 years instead of the 35 years the Voyagers needed. 15 instead of 35. And so the question becomes much, much bigger than just, can we build it? Whoever builds Voyager 3 first will not just be sending a spacecraft into the dark. They will be choosing which culture, which language, which message represents Earth in interstellar space for the rest of human history. And so we arrive at the heart of it. What separates Voyager 3 from its predecessors is not just better technology, it is a completely different philosophy of how to leave home. The original Voyagers were sprinters that happened to find a hill to roll down. They got one good launch, picked up free momentum from the planets, and have been coasting ever since. Their speed, impressive as it is, has not changed meaningfully in 40 years. Not meaningfully. Once they crossed Neptune, they were essentially passive objects traveling on inertia alone. Voyager 3 would be the exact opposite. A spacecraft built to keep pushing for years, building up its speed across the entire mission, while remaining completely free to pick its own direction. Less of a probe in the old sense, more of a long-distance vehicle that builds its momentum the same way an ocean liner does, slowly and patiently, without ever needing to ask the planets for permission. And here's where it gets really exciting. Within 30 years, it could be moving faster than Voyager 1 has ever traveled. Within 60 years, it could be deep into interstellar space, with fuel and power to spare for instruments still running, still transmitting, still calling home. Without a chemical rocket gulping all its propellant in the first single hour, the lifetime of the mission becomes a question of how long the reactor lasts, not how fast the fuel runs out. The reactor. Friends, the era of waiting for the planets is ending. The age of patient acceleration finally is beginning. And you, if you could choose the destination for the first ion-powered Voyager 3, where would you point it? Toward the center of the galaxy is one option. Some of you might prefer the dark inner arm regions, far from any star. Others might want to send it straight up out of the ecliptic toward the solar pole no human or robot has ever flown before. Tell me in the comments. I genuinely want to know, and I read every single one. And if you want to understand why, despite all this technology being ready, despite the engineering being feasible, no agency has officially announced a Voyager 3 mission yet, watch Why Didn't We Plan a Voyager 3 Yet next. It's the perfect companion to this video, and it explains the political and financial side of the story that the engineering alone simply cannot answer. See you over there.